In this video, we're going to give you an example of how you can use the conservation of energy for a closed system to solve a problem involving moving boundary work. So to do that, we're going to use example problem 3.2. Okay. And in this problem, we are given that we have an air in a piston cylinder device. It has initial pressure of 100 kilopascals, specific volume of 2 meters cubed per kilogram, and it goes through an isobaric process involved with a shaft providing 40 kilojoules of work to the system until the volume triples. Internal energy increases by 215 kilojoules during the process, and they want to know the heat transfer associated with the process, neglecting kinetic and potential energy. So what we know is that we have air in a piston cylinder, and it's undergoing, an isobaric process. Oh, excuse me. Let's go back there. Isobaric process. Okay. All right, and what they want us to find is the heat transfer associated with process. So they want to know what the heat transfer is. Remember, previously our heat transfer we used the letter Q. So we're going to say Q of the process. So our process we're going to say is from 1 to 2. And they want to know that in kilojoules. So we'll just put next to as a reminder, we want our units to be kilojoules. Okay. Now let's look at this diagram and data we have here. I've already taken the liberty of putting this on. So here you can see all the information we have. We have the mass of the air in this closed system. We have the pressure. Initially and final, it's isobaric, so they're the same. We have the specific volume, and we noted that after the process, it's going to be 3 times as much. We have shaft work. Now remember, due to our nomenclature, hip to win, when we say work in is negative, so this shaft work, the work is coming into the system, so we've designated that a negative 40 kilojoules. We don't know the internal energy at each state, but we do know the change in the internal energy is going to be 250 kilojoules. And that's about it. Okay. So let's list our assumptions. So let's see our assumptions we're going to state. We're going to say it's a closed system. We're just assuming that no air was able to get out. Another way you can abbreviate saying that it's a closed system is you can just put the mass, circle it, saying that the mass is constant. All right. They've told us we're going to neglect potential and kinetic energy changes. So the way we write that is we say the change in kinetic energy and the change in potential energy are both negligible or close to 0. This is a reasonable assumption because if you think about it, we can just assume they don't tell us what the velocity is of the piston beforehand or the system, but you can assume that since they don't tell you anything, we'll just say that it stopped beforehand and it stopped at the end. Therefore, the change in kinetic energy will be 0. And air over that short distance, there's not going to be a lot of potential energy for the air changing over that short distance, so we can treat that as negligible as well. So now we're ready to start the analysis. So the equation we're going to use is the one we've derived previously for conservation of energy for a closed system. It's equation 3.10. It's also on your reference data card. So we're just going to write it out here. In respect to the process 1,2, we're going to say the heat transfer 1 true minus work 1,2 is equal to, and we normally put the mass in front But since they're given the internal energy in the actual internal energy, not the specific internal energy, I'm going to go ahead and just write internal energy 2 minus internal energy 1. So this won't be in the specific form, this will be in the actual total form. Plus, well, it's our changing kinetic changing potential energy, but we've already said that's going to be 0, but we're just going to write it out. Mass velocity 2 squared minus velocity 1 squared plus mass times gravity times height 2 minus height 1. All right, because of our assumptions, we're going to go ahead and say that this term are 0. So now we're left with just 3 terms, our heat transfer, our work term, and our internal energy. Now recall they said that they gave us the value for internal energy. So we can rewrite this as transfer minus our work is equal to 215 kilojoules. Okay. So now what we're going to do is we're trying to solve for heat transfer. Let's put this on one side. We got our heat transfer 1, 2 is going to equal our work 1, 2 plus 215 kilojoules. All right, so we mentioned this as a note in a previous lecture, but when we say the work in this equation, it includes all possible work. So in this case, we have 2 types of work. We have the shaft work, so let's look up here at the diagram again. We have the shaft work of the work coming in, right here. So there's that shaft work, but we're also going to have a moving boundary work, because if you look, we got the piston moving up, right? So if we have a change in volume, so we have this original volume, it's going to change going up to there. And we also remember that we did say that this is an isobaric process, right? So knowing it's an isobaric process, we know that we can write it as the pressure times the change in volume. Okay. So let's break out these works. Oh, excuse me. Let me change that back to black. So heat transfer is going to equal, and we'll write this out first as work 1, 2 shaft plus work 1, 2 moving boundary plus 215 kilojoules. All right. That shaft work we already have. Now remember, like we said, work in negative. So we're going to say that it's a negative 40 kilojoules. And our boundary work, taking from that definition, we said that for an isobaric process, it's pressure times change in volume. We've got our pressure times volume. Put these little serifs on top to make sure it's volume. Volume 2 minus volume 1. Plus 215 kilojoules. All right. Now, we can go ahead and sum the 215 plus the negative 40, which is going to give us 175 kilojoules. And looking at what we have, so the pressure we're given as 100 kilopascals. And then we got these volumes. So we don't exactly have the volumes, we have the specific volume. Remember, specific volume is just volume by mass, and we already have the mass, and the mass is constant. So we can get the volume then, right? So I'm going to do is, since the mass is constant, I'm just going to pull it out and say we've got mass 0.5 kilograms. All right. And then we're going to multiply it by the change in volume. So we know then that specific volume 2 is equal to 3 times specific volume 1, and specific volume 1 is 2 meters cubed per kilogram. So we could do that, we could break it down to uh, by doing 3v1 minus v1 gives you 2v1, or we could just rewrite it saying that 3 times 2 is going to be 6, so 6 meters cubed per kilogram minus 2 meters cubed per kilogram. Either way makes sense to you. That's the difference between these specific volumes. Okay. So we have 175 kilojoules. The kilograms above here are going to cancel out. What we're going to get then is 100 times 0.5 times 4. 100 times 0.5 is going to be 50. Times 4 is 200. We've got plus 200. And let's look at what units we have here. So we're going to write as kilopascals meters cubed. All right. So what is that unit? Well, sometimes it's easier if we look at what are some of these more complicated units break down to. So let's look at kilopascal. Another way of saying a kilopascal is that you can say it is 1 kilonewton per meter squared. Okay? So we're going to say kilonewtons per meter squared. Well, if we do that, these kilopascals cancel out. And the meter squared cancels with the meter squared from here, and so we're left with meters. So what we're going to get is a kilonewton times a meter. Now, if we look at the definition of a joule by definition is a newton meter, newton times a meter. So then a kilonewton, which is just 1,000 newtons, times a meter is going to be 1,000 joules, so a kilojoule. So we have that this is actually equal to kilojoules. Just to be even more clear, I will write that out. So we have that a kilonewton times a meter is the same as a kilojoule. And you can get some of these relationships on the back of your text. So then our kilonewton and the rest of our meters cancel out, and we're left with kilojoules. All right, so what we get is 175 kilojoules plus 200 kilojoules. So what that comes out to be is 375 kilojoules. So that's our heat transfer 1, 2. You can note that it is a positive resulting answer based on hip to win. That means that if it's positive, the heat going in is positive, so this heat will go into the system. So in order for this energy to balance, so looking up at the system here, in order for the volume to increase by 3 times with this shaft work coming in, right, and this change in internal energy, in order for it to balance based on this conservation of energy equation we have right here, then we are going to have to supply a heat transfer of 375 kilojoules. Okay. Hope this helps. There are more example problems in your book, and we'll also have the study guide problems as well to go over to help you out.